We now discuss the solution of a problem from the section analysis, and this question is on the properties of a subset of R square. This question has appeared in CSIR National Eligibility Test held on 26th November 2020, and it is from the section C. The problem is: consider the subset of R square defined as follows. Capital A is equal to the set of all those ordered pairs x comma y belongs to R cross R, where R is the set of real numbers such that x minus 1 into x minus 2 into y minus 3 into y plus 4 is equal to 0. Which of the following statements are true? The four options are given. Option 1, A is connected. Option 2, A is compact. Option 3, A is closed. Option 4, A is dense. And if you observe, the options 2, 3 and 4 are based on closed nature of A, and option 1 is about the connectedness of A. So we will first talk about the connectedness, then talk about the closed, and then subsequently talk about 2 and 4. So we have A is a subset of R square, and A is the set of all ordered pairs x comma y belongs to R square such that x minus 1 into x minus 2 into y minus 3 into y plus 4 is equal to 0. Now, if I take the ordered pair 1 comma y, where y is any real number, it satisfies this equation, and hence 1 comma y belongs to A. And so also 2 comma y belongs to A for all y belongs to R. And in a similar way, we can also talk about x comma 3 ordered pairs, and we see they all belong to A for all x, and so also x comma minus 4. So they all belong to A for all x belongs to R. So now let A1 is equal to the set of all ordered pairs 1 comma y, y belongs to R. What are they? They are that is the set of all points lying on the vertical line x is equal to 1 in R square. A2 is the set of all ordered pairs 2 comma y, y belongs to R. And what are they? That is the set of all points lying on the vertical line x is equal to 2, and they are shown here. So x is equal to 1, the line, x is equal to 2, the other line. Now, A3 is the set of all those ordered pairs x comma 3x belongs to R, that is the set of all points lying on the horizontal line y is equal to 3. Similarly, A4 is the set of all x comma minus 4 belongs to this A, where x belongs to R, and that will be the set of all points lying on the horizontal line y is equal to minus 4. So A3, this is the horizontal line, that is y is equal to 3, and this is y is equal to 3, and this is y is equal to minus 4. This we call it as A3, this we call it as A4. And now we see A1 union A2 union A3 union A4 is precisely capital A. So we continue. We first take the statement given under option 1. A is connected. We see whether it is true or not. We have A is equal to A1 union A2 union A3 union A4. The diagram is given here. And note that each AI, that is A1 is connected, because it is you can A1, A2, A3, A4, they are all connected. Why? You can see each is a straight line up to extended up to minus infinity to plus infinity, minus infinity to plus infinity, and in this case also minus infinity to plus infinity. It is just like a R, minus infinity to plus infinity, which is connected. So note that each I is equal to 1, 2, 3, 4 R is connected. Now we recall a result. The union of two connected sets will be connected if they have a non-empty intersection. So having non-empty intersection is connected. So what we do is A3 is connected, A1 is connected, but they have a non-empty intersection 1, 3. Therefore, A3 union A1 is connected. So A3, A1 are connected. Their intersection is the singleton 1, 3, which is not empty. By using this result, A3 union A1 is connected. Now, take A3 union A1, which is connected, and A4 is connected, and their intersection, A3 union A1 intersection A4, is a singleton set, that is 1, 4, which is not empty. So A3 union A1 and A4 are connected. If you take their intersection, it is not empty. Therefore, A3 union A1 union A4 is connected. Now, A3 union A1 union A4 is connected, and A2 is connected, and their intersection consists of precisely two elements, that is 2, 3 and 2, minus 4. That is not empty. And hence, A is equal to A1 union A2 union A3 union A4 is connected. So, the option 1 is true. We move on to the third option. So, the statement given under third option is A is closed. Now, we have this A1 union A2 union A3 union A4. Let's look at the figure. Now, it may be noted every point of A1, we talk about A1 first. If you take any point on A1, that is a limit point of A1. Why? If you take a point, any point on A1, and take any neighborhood, every neighborhood of that point will contain infinitely many points of A1. And here neighborhood is a circular neighborhood because the situation is in R square. So we talk, this is the point, arbitrary point, and every neighborhood of that will contain infinitely many points. Therefore, that point is a limit point. So every point of A1 is a limit point of A1. But instead, if you take a point not on A1, you can always draw a circular neighborhood in such a fashion that it has nothing common between the points of A1. So, any point not in A1 is not a limit point. So take this point, and we can always draw a neighborhood around it, and which have nothing common between this set of elements and A1. And hence, that point is not a limit point. That means any point not in A1 is not a limit point of A1. So thus, A1 contains all its limit points. Therefore, A1 is closed. In a similar argument, you can also say A2, A3, A4 are closed. And we say A1 union A2 union A3 union A4 is also closed because the union of finite number of closed sets is closed, and hence A is closed. Now, A is equal to A1 union A2 union A3 union A4 is closed. Why? Because the union of any finite collection of closed sets is closed, and hence A is closed. The option 3 is true. We move on to the second option, and the statement is A is compact. So we have that A is equal to A1 union A2 union A3 union A4. So and clearly each ai I is equal to 1, 2, 3, 4 is unbounded. Take a1, a1 is unbounded, so it is extended, minus infinity plus infinity on the y-axis, on the ordinate side. So it is unbounded. So a1 is unbounded, a2 is unbounded, a3 is unbounded, a4 is unbounded. Each one is an unbounded set. Suppose that this a is equal to a1 union a2 union a3 union a4 is compact, and a is compact where in R square. In R power k, a subset of R power k is compact if and only if it is closed and bounded. So this implies A is closed and bounded. Why? Because a subset E of R power k is compact if and only if E is closed and bounded. So that means A is bounded. So A is bounded, and we have AI is a subset of A. Therefore, AI is also bounded, but it is not. We get a contradiction. So, because of this contradiction, that A is compact is not true. So, therefore, A is not compact, and hence the option 2 is not true. So, we are left with one more option. Let's go. Option under 4, that A is dense. We have A union of A1, A2, A3, A4, and now note that A is not equal to R square. Why? A1 points on A1, points on A2, points on A3, points on A4 will not exhaust all the points of R square, and A is a proper subset of R square. A is not equal to R square. And because A is closed, A bar is equal to A. A is closed if and only if A closure is equal to A. A bar, A closure is equal to A. So A closure is equal to A. Suppose that A is dense in R square. If A is dense in R square, A closure must be equal to R square. But this implies A bar is A is equal to R square, which is a contradiction, because A is not equal to R square, a contradiction. Therefore, A is not dense in R square. Thus, the option 4 is not true. So, in all, how many are true? So, the options are there. 1 and 3 are true, and 2 and 4 are not true. Our final answer is the options 1 and 3 are true. That is the discussion of the solution of the problem about the properties of subsets of R square. And it is an interesting problem from analysis. I hope that you have understood the argument and the solution of this problem. I wish you all the best. Thank you.